All right. So if you can hear me, let's start.
Yes, we can hear you, teacher.
All right. So 6.1, chapter 6, section 1 is about how to induce an EMF, electromotive force. Uh, First, I will define what EMF means. Electromotive force means any device which produces electrical energy, any device which produces electrical energy is defined as a source of electromotive force or source of EMF. And this EMF, sometimes abbreviated by just E, epsilon, so representing EMF. We can provide electrical energy by two methods. One of them is we use chemical batteries. So electrical energy is provided by chemical reactions. You have maybe you saw so many batteries. So on uh, each surface, on the surface of the battery, written what is EMF value, what is the potential difference of this battery. EMF of this battery, for example, 1.5 volt, which is written on the surface. This 1.5 volt means terminals of the battery. So one terminal is positive, other terminal is negative, and the positive terminal is 1.5 volt higher potential than the negative terminal. And this battery is represented by like this. So one terminal is positive, which is higher potential. The other terminal is negative, which is lower potential. And the potential difference between these two terminals is 1.5 volt. This is the symbol of a DC EMF source, DC battery, direct current in an electrical circuit. Second method is electromagnetic induction. So we are going to use a technique in physics by using some physics laws, and we will induce an EMF. We are going to get electrical energy to use in our devices. This is the second method. So we will talk about this one, of course, more frequently than that. So batteries, we know that supplies electrical current to a conductor by producing a potential difference between the ends of the conductor. So if there is no potential difference between the ends of a conductor, there will be no electric current. So the reason of the electrical current or cause of electric current is potential difference. So a battery supplies that. A battery has a positive terminal, as I said, a negative terminal, and then there's a difference in potential between these two terminals. When you connect this battery to a conductor, say that this conductor is AB, A side is attached to the positive terminal of the battery, B side is attached to the negative terminal. Of course, whatever the potential difference of this battery is, this conductor will have the same potential difference, 1.5 volt. So that's why an electric field will be formed from positive end of the conductor to the negative end. So an electric field is formed from positive to negative within the conductor. And this electric field sets charges into motion. In the chapter 5, section 3, we talk about that. Magnetic field cannot set charge into motion, but electric field can do that. That's why this electric field within this conductor sets charges into motion, starts charge moving. And there could be two possible charges in a conductor. One of them is positive charges. These positive charges move in the same direction of this electric field. Second one is negative charges, which moves in the opposite direction of electric field. So these motions, these two types of motion of these two types of charges produces a conventional electric current, and this electric current direction is chosen in the same direction of the electric field. So then we say that yes, this positive discharge, this potential difference between the ends of the conductor causes an electric field to be formed, and from positive to negative, and this electric field produces an electrical current, again from A to P, from positive to negative. That's why we can say that yes, electric field direction and electric current directions are the same in a conductor. And in chapter 5 section 3, we give some electrical current to a wire in a magnetic field, remember, and this wire experiences a magnetic force and set the wire into motion. And we got motion from electric current in chapter 5 section 3. We converted electrical energy to mechanical energy in chapter 5 section 3. Examples, for example, galvanometer, it was rotating when electric current is given, or loudspeaker, when electric current is alternating electric current is supplied to the coil, it was vibrating, or electrical motor we will study in section 2. All these are converting electrical energy to mechanical energy. But right now in section 1 chapter 6, we will now set a wire into motion. We will set it how? By pulling. We will we will pull a wire inside an external magnetic field. Of course, by applying some force, you should do that in a magnetic field. And we will see that, we will observe that this wire produces electrical current. So here's chapter 6, section 1. We will convert mechanical energy to electrical energy. It is opposite process of chapter 5, section 3. So mechanical energy will be converted to electrical energy by pulling a wire inside a magnetic field. Inducing, which means producing electric current by using the magnetic field or by using the change in magnetic field, is called electromagnetic induction. Now we will do that. So pulling a conductor perpendicular to a magnetic field. Pull a conductor perpendicular to a magnetic field so that the conductor crosses magnetic field lines. Look at here. Here, a magnetic field is given into the page, cross into the page. And there is a wire located inside this magnetic field, and you are pulling this wire perpendicular because this wire is moving in the plane of the page, parallel to the plane of the page, and then magnetic field is into the plane of the page, which means this wire must cross these magnetic field lines as it is pulled to the right. For example, I first pulled this conductor to the right. So when we pull this conductor to the right by my hand, I pull it. We know that in a wire, electrons are mobile, which are free to move, but protons are immobile, which is kept in nucleus. These electrons, this electric current is provided by motion of the free electrons in a conductor, in this conductor. When conductor is being pulled perpendicular to the magnetic field to the right, we pull this conductor to the right. Of course, electrons are also moved together with the conductor. When we are pulling this wire to the right, these electrons on the wire also pull to the right. If a charge is moving perpendicular to magnetic field, if you move a charge perpendicular to a magnetic field, there will be a magnetic force acting on this charge. We can find the direction of this magnetic force by applying right-hand rule. So magnetic field is into the page. So you are going to show your forefinger into the page. Do it now, it's into the page. And you pull the wire to the right. Your thumb must point to the right. In this case, you are going to observe that your palm is pointing the upper end of the conductor, but opposite of your palm is showing or pointing the lower end of the wire, which means force acting on the electrons will be down to this plane of the page. That's why these electrons on the conductor will start moving to the down to the lower end. This end will be negatively charged because electrons are living here. So upper end will be positive charge. So electrons accumulate at the lower end according to this picture, and of course upper end, other end becomes positive. So if we look at this conductor, we can see that there is a potential difference. There's a potential difference created between the terminals of this conductor. One end is positive, other end is negative. It is just like a battery. Battery also has a positive terminal and negative terminal, which means if you pull a wire inside a magnetic field by your hand or by some other uh, sources or some other devices, some other methods, a potential difference or an electromotive force is induced between the ends of this ends of this conductor, and this conductor acts like a battery. If electrons are moving down to the plane of the page along this conductor when you pull it, which means electric current must be up to the plane of the page, because we know that electron motion and electric current directions are assumed to be in opposite directions. This is the general assumption of electric current. So direction of the electron motion is down to the plane of the page, but in this current must be up to the plane of the page. And of this electromotive force, in this electromotive force, potential difference, other name of the potential difference right now, called electromotive force. This induced electromotive force in the conductor, which is pulled perpendicular to magnetic field, depends on three physical quantities. One of them is, of course, magnetic field. If no magnetic field, you cannot cause a force acting on electrons. Second one is length of the conductor. If you use a longer conductor, which means there are more electrons. If more electrons, the induced EMF will be greater. Third one is the speed of the conductor that is pulled. So how fast you are pulling this conductor inside a magnetic field also determines the induced EMF. And equation for induced EMF, E, induced EMF between the ends of this conductor, is calculated by equation B times L times V. So sometimes, as you say, it's equation believe. Equation is believe. So this is the equation how we calculate how much EMF can be induced between the ends of the conductor. And of course, this polarization can be changed. So in the first case, when we are pulling it to the right, so upper end were positive, lower end were negative. But if you pull it in opposite direction to the left, again, if I apply the right hand rule, four fingers are into the page. Thumb is showing to the left because you are pulling the wire to the left. This time, palm is pointing lower end, but opposite of your palm is pointing upper end. So then, which means you can change the polarization of this wire, and you can change one side negative, other side positive by reversing the direction of the pull. So if you pull it to the left, so then polarization changes. So if the direction of the pull of the conductor is reversed, electrons will be pushed upwards. Polarization of the conductor changes. So then direction of the induced current also changes. Here, induced current was up to the plane of the page because it is opposite direction of the electron motion. But here, induced current is down to the plane of the page because it's also opposite direction of electron motion. And second thing which can change direction of polarization is the magnetic field. Here is the magnetic field is into the page, which is cross. If you make this magnetic field for this picture out of the page, again, you will observe that polarization changes. This is going to be positive, that is going to be negative in this case for this conductor, which is pulled to the left. And this is the first method of electromagnetic induction, but this is not so practical way. That's why we will talk about another method right now. It is second method of inducing EMF is using a loop. It's a wire, like a circular wire or a rectangular wire, by changing the magnetic flux through the loops. So this is the second method. Uh, in this case, we should change the magnetic flux. So magnetic flux through a coil or a loop can be changed by three ways. How we know? Because according to the equation of magnetic flux, A times B times cosine theta, A can be changed, so B can be changed, or theta can be changed. So then we can change the magnetic flux. So one of them is changing the B, which is the change in magnetic field strength B through the loop. Second one is changing the area of the loop through which magnetic field line passes. Third one is changing the angle, which is orientation of the loop with respect to magnetic field. So now we will study this one by one. The first one, uh, by changing magnetic field strength B through the loop. How can we do that? Now here, uh, a bar magnet and a loop are at some distances. But if you initially, let's count the magnetic flux through this loop, just number of lines crossing the area, 1, 2, 3, 4, and 5. Magnetic flux at this distance, at this separation, is 5 Weber. But when you move this loop and this magnet closer, so as you see, magnetic flux is changing. It becomes 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So magnetic flux has increased. Magnetic flux has changed. So when magnetic flux is changing, because you are moving this bar magnet and the loop relative to each other, you can make them approaching or you can make them moving away. Both cases, and if you move them relatively one another, so then you are going to induce an EMF on this loop, and you will see that there is some currents, some electrical energy starts to circulate on this loop. This is the first way. But be careful, when you are moving the loop, the plane of the loop mustn't be parallel to magnetic field lines. If it is parallel, if this line does not cross the area, so magnetic flux becomes zero here. When you move, again becomes zero. That's why you shouldn't hold the plane of the loop parallel to magnetic field lines. If you hold it parallel and if you move it parallel to the magnetic field lines in when in and out, so then there will be no change in magnetic flux for these two cases. There will be no induced EMF for these cases. There's a good example, conceptual challenge example in your book. Suppose you are wearing a bracelet that is an unbroken ring of copper. If you walk briskly directly into a strong magnetic field while wearing the bracelet, how would you hold your wrist with respect to magnetic field in order to avoid inducing current in the bracelet? Yani, it says you are going to enter inside this magnetic field with a bracelet, and there will be no current, no induced EMF on this bracelet. How can you do that? If you hold the bracelet, of course, parallel to the magnetic field lines, so when it was outside, magnetic flux is zero. Even when it's entering inside, magnetic flux is zero, because parallel, the plane of the bracelet is parallel to the magnetic field. Then there will be no crossing the area, so then there will be no change in the magnetic flux. If no change in the magnetic flux, so no current is induced. So that's why you should hold this ring or this bracelet parallel to magnetic field lines to avoid some current to be induced when entering or leaving this magnetic field region. Second one is we are going to change the area, changing the area of the loop through which magnetic field line passes. To do that, move a loop into or out of the magnetic field region, but perpendicularly. But perpendicularly, not parallel. If you move parallel again, so there will be no change because always magnetic flux will be zero if you move parallel to the magnetic field lines. So if you enter inside a magnetic field perpendicularly like this, initially, loop is outside. And then you start pulling this loop to the right, and magnetic field here in this region is given into the out of the page, which is dot. But initially magnetic flux is zero. Then you start pulling this loop into the magnetic field region. So as the loop is entering inside a magnetic field region, magnetic flux increases because initially zero, then it gets a value. magnetic flux increases. As magnetic flux is changing, we know that there must be an induced EMF. As this loop is entering inside a magnetic field, there will be a change in magnetic field. There will be an increase in magnetic flux. So that's why there will be an induced EMF, which is circulating on this loop, or on this loop. Or when you are pulling it out of the magnetic field. So it is initially inside a magnetic field, magnetic flux is maximum, but when you take it out of the magnetic field region, what is now here magnetic flux? Zero, from maximum value to zero value. So the magnetic flux decreases here. Again, magnetic flux changes. That's why here and here, when entering a magnetic field region perpendicularly or leaving a magnetic field region perpendicularly, so there will be a change in magnetic flux. There will be an induced current or induced EMF on this loop. But in here, when it's moving inside a uniform magnetic field, but uniform, which means magnetic field intensity is the same everywhere. So separation between the lines is the same everywhere. So here is the magnetic flux: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Here's, if you count, it's also 15. When you are moving as this wire perpendicular to magnetic field inside a uniform magnetic field, there will be no change in magnetic flux. Magnetic flux will be the same. If the magnetic flux doesn't change, it is impossible to induce an EMF. That's why in this wire, in this loop, there will be no induced EMF as it is moving inside a uniform magnetic field perpendicularly. This is also not the case, which does not result in an induced EMF. So that's why you should pull a loop into, or you should pull a loop out of the magnetic field to induce an EMF. Third, third one is changing the orientation of the loop, which is the angle. You are going to change the angle with respect to magnetic field lines. Like this, and there is a coil. This coil is initially parallel to the magnetic field lines, but you are rotating this coil inside a magnetic field. When it is parallel to magnetic field lines, so what? Magnetic flux is zero. Then you start rotating it, and then you made it perpendicular to the magnetic field line. So maximum number of the lines are crossing the area. So magnetic flux is changing, yes. So that's why this change in magnetic flux induces an EMF on this coil. So by changing the orientation of the loop, yani angle with respect to magnetic field lines, so to do that, rotate the loop inside the magnetic field. This is the title we will study in section 2. It is there because it is the most practical way. It is the methods of generators, how generators induce EMF in a magnetic field. And what chapter 2 questions talking about this one? So you can rotate the loop inside a magnetic field, or you can rotate a magnet inside the loop. Both are, in fact, causes a change in magnetic flux. So a bar magnet is attached to the perpendicular to rotating shaft. So this is the shaft, which can rotate about its own axis, and a magnet is attached to this shaft again. So together with the shaft, this magnet can rotate. The magnet is then placed in the center of a coil of wire. Yes, as you see, this magnet is in the center, inside the coil of the wire. In which of the arrangement could the device be used as an electric generator? Yani in which cases, this or this or that, so there is an induced EMF in this coil. We are going to try to get this. Of course, induced EMF can be observed if there's a change in magnetic flux. So you are going to think that when you are rotating this bar magnet inside this at the center of this coil, if you make a change in coil through this change in magnetic field flux through this coil, then you can say that there will be a induced EMF. Initially, this magnet is parallel to the plane of the loop. So then all magnetic field lines are parallel to the magnetic plane of the loop. If parallel, so there will be no magnetic flux, initially zero. But when you rotate this shaft, this magnet turns like this. So it becomes N pole and S pole, initially showing in this direction, in vertical direction according to page, up to the plane of the page. But when you rotate it, so N pole becomes into the page, S pole becomes out of the page, which means magnetic field direction it becomes perpendicular to the magnetic field, perpendicular to the area of the loop. So which means magnetic flux is changing. When you're rotating this bar magnet inside a magnetic field, as in A, magnetic flux is changing. If magnetic flux changes, so then there will be an induced EMF. Second one, initially magnetic field lines are again parallel to the plane of the loop, so zero magnetic flux. But when you rotate it like this N pole shows into the page, S pole shows out of the page. Again, magnetic field lines becomes perpendicular to the plane of the loop. So it was initially parallel, but then becomes perpendicular. So for that reason, magnetic flux changes. So induced an EMF. This is also can be used as a generator. But in C, when you rotate it like this, initially N pole is and S pole, it's parallel. So magnetic fields of the magnet is parallel to the plane of the loop. Then when you rotate it like this, N pole shows up to the plane of the page. S pole shows down to the plane of the page. Again parallel. So when you make this magnet like this, so it also becomes parallel to magnetic, so parallel to the plane of the loop. So there will be no change in the magnetic flux. There will be no induced EMF in this coil. So C cannot be used as a generator, but A and B can be used as a generator. And we will advance a little more. Uh, Now we will talk about the induced magnetic field. In this magnetic field, first we know that a bar magnet has its own magnetic field, which is known as external magnetic field. Assume a bar magnet is being pushed into a coil of wire, a coil of the wire. If there's relative motion between the magnet and the wire, so we will say that on this wire there will be a current. A current is induced in the coil. We know about this. And this current also must have its own magnetic field. So this induced current produces its own magnetic field, which is known as induced magnetic field. So then we can say that if a bar magnet and a coil are relatively approaching or relatively moving away, there will be two magnetic fields. One magnetic field is bar magnet's magnetic field. Second magnetic field is current, induced current magnetic field, which is known as the induced magnetic field. And like this. Now I am going to explain right here. As I said, the bar magnet, this bar magnet has its own magnetic field. We said it's the external magnetic field. If this bar magnet and the coil are relatively approaching or relatively moving away, there will be an induced current on this coil, and this coil will have its own magnetic field, which is known as induced magnetic field. So we will study two cases. If coil and magnet approaches, first we will study this. If this coil and this magnet relatively approaches, as I showed the direction of V to the left. Yeah, and this bar magnet is approaching to the coil. So if a coil and a bar magnet approaches, or a bar magnet is approaching to a coil, or a coil approaching to bar magnet, so relatively approaching means this. A pair of forces that repels each other is created between the coil and bar magnet. Yani these coils magnetic field and this bar magnet's magnetic field repels each other. So this is the end pole of the magnet. So this pole must be N so that N and N can repel each other. So approaching, in the case of approaching magnetic field, N pole is approaching, the coil's closer end will be N pole, opposite and the farther end will be S pole, N pole and S pole. But if S pole is approaching, S pole is approaching to the coil, so they must repel each other. S pole of the bar magnet is repelled by S pole of the coil. So in this case, closer end of the coil will be S pole and opposite end or farther end will be N pole. So this is so easy. Just when you, then you can say if in the case of approaching, these poles will be opposite, unlike like poles. Yes, to repel each other. N and N or S and S. But if a bar magnet recedes from the coil and moves away, in this case, a pair of forces that attracts each other is created between the coil and bar magnet. So as you see, V is to the left, so to the right, which is this bar magnet is receding, moving away. In this case, force between these two poles must be attractive. How? If this is N, that must be S. If this is S, opposite far N must be N, unlike poles. If S is moving away or receding, if S is to be attractive, if this is S, that must be N, and this is N, this must be S. So this is the way how we determine the uh, poles of the magnetic field on this coil. So according to relative motion of a bar magnet, we can find it, we can get it. And uh, next step is to get the direction of the current on this coil. So we got the direction, where is the N pole and where is the S pole. So as it is, for example, as S is receding, this must be N pole. So this must be S pole. So if it is N pole, this N pole must be produced by some current on these loops of this coil. So now next step is, what is direction of the current on these loops of this solenoid or on this coil? Again, we will use the right hand rule we used in section 2, chapter 5. Remember, for a coil or a solenoid, curled forefinger was representing the electric current on the solenoid. Thumb was pointing the N pole. But this time we know where N is. First we will show N pole with our thumb, and after that we will decide direction of the electric current on this coil. So, for example, if this bar magnet is receding, moving away, we saw that N pole points to the coil, so closer end of the coil must be S. If this is S pole, other side must be N pole. So your thumb must show the N pole. Right hand rule again we are applying. Thumb must pointing the N pole. In this case, curled forefinger is representing direction of the electric current on the coil or on the loops of this coil. So then you are going to follow the wire. So if the electric current is going this direction, it must come back from behind, follow the wire. It must be from right to left on this resistor. And let's apply another case. For example, here S pole is receding. S pole is receding. So this must be N pole. The S pole is receding. This must be N pole. If N pole is this, hold your thumb to the right and curl your right hand and make your thumb is pointing to the right, which is N. And curled forefinger, you are going to observe that it's coming like this. So from behind to front on the turns of the coil. So follow the wire from behind to front, follow the wire. It must be from left to right on the resistor. Another example here. So S pole is approaching in this example. S pole is approaching. If S is approaching, this must be S, because they must repel each other. A pair of force repelling each other is created, but still you are pushing it. You are pushing it to the right, to the left. If this is S, that must be N. So hold your right hand so that your thumb is pointing to N pole. Curled forefinger will show the direction of the electric current on these turns, which is from front to behind, from front to behind, front to behind. Follow the wire. So it must be from right to left on this resistor. So generally the question will be asked on this resistor, what is the direction of the electric current? From right to left or from left to right? And this is how we find the direction of the induced current on a coil when a bar magnet and the coil are relatively moving each other. But in fact, the method of finding direction of the induced current on a coil is known as Lenz law. Lenz law. It's the rule. Finding the direction of the induced current is called Lenz law. So Lenz law is application of Lenz law to these problems are a little confusing. That's why this method is better one. But we should know what Lenz law is. What does it mean in fact? Lenz law states that magnetic field of the induced current in a coil is in a direction. Yes, Lenz law is about the direction of magnetic field. So direction of the induced current, it's about that. Magnetic field of the induced current, and it's about the induced magnetic field direction. Lenz law is about induced current direction. It must be in a direction that opposes the change. So keyword is opposing the change, not opposing something. If something is changing, this change opposing the change in applied field, opposing the change in external magnetic field of the bar magnet. So which means this change can be increasing applied field or decreasing applied field. So if increasing applied field, how can you oppose an increase in applied field? By producing an induced magnetic field that is in opposite direction of the external magnetic field. So increasing applied field, increasing applied field can be opposed by an induced magnetic field that weakens applied field by being in the opposite directions. But if applied field is decreasing, how can you oppose that decrease? Of course, by supporting. Induced magnetic field supports the applied field by being in the same direction. Of course, supporting. If you want to support a vector, you must be in the same direction. If you want to oppose an increasing magnetic field, you should be in opposite directions. As a result, the total magnetic field strength in a region between a magnet and coil keeps constant according to energy conservation. Now I'm going to apply this method too, but as I said, this is the easiest one, but I will also apply Lenz law on to get the direction of the magnetic field and the induced current on this coil. For example, assume that a bar magnet with N pole is looking to the coil, S pole is opposite, and then receding, it's moving away. So then I'm going to choose here a region, a point. In this point here, this bar magnet N pole produce a magnetic field to the left because magnetic field lines are leaving from N pole. We know about this. So then magnetic field direction of the bar magnet at that point is to the left. But it is receding magnet. If it is receding, this blue magnetic field, which is to the left, is decreasing because bar magnet is moving. If it is decreasing, magnetic field of the coil must support that. So opposing the change. Here is change is decreasing. So then this magnetic field of the coil is supporting this blue magnetic field, which is the bar magnet's magnetic field. They will be in the same direction in this region. If this magnetic field is to the left too, follow magnetic field direction to the left, to the left, to the left, to the left. So it's entering to the coil. So which end is this in this case? Magnetic field enters to S pole. So this must be S pole of this coil. Then according to this, you can find direction of the magnetic electric current on the coil by using right hand rule. If this is S pole, that must be N pole. Hold your right hand so that your thumb is pointing to the left, which is N. Curl your forefinger, which is going to be from front to behind, front to behind. Follow the wire. It's going to be from right to left on this resistor. Let's apply it to the second example. A bar magnet is approaching magnetic field here. In this case, here blue magnetic.
Evet.
Tamam, o zaman başlıyoruz. Okay, so as I said, yes, when when this bar magnet is approaching to the coil, so then in this case, blue magnetic field in this region, which is to the left, is increasing. That's why magnetic field of the coil must be opposite in direction to the right. If it is to the right, which is leaving from this end, so magnetic field leaves from which end? Of course, N. So this must be N pole. That must be S pole. According to that, you are going to apply the right hand rule to find the induced current direction on this coil. And this is the Lenz law, how we apply the Lenz law. And there's an example about this conceptual challenge, which says that a bar magnet is dropped towards the floor on which lies a large ring of conducting metal. The magnet's length and thus the pole of the magnet is parallel to the direction of motion. So it's falling down so that N pole or S pole is aligned like this, not horizontal, it's falling, vertical, it's falling. Disregarding a resistance, does the magnet during its fall towards the ring moved with the same constant acceleration of free falling body? Question is this: when the bar magnet is, of course, falling towards this ring, so then there will be an induced current and induced magnetic field of this ring because N pole is approaching and this pole is approaching. So this ring must polarize so that upper side is N, lower side is S. This N and this N will slightly repel each other. For that reason, this bar magnet will fall down with a gravity less than free fall. And there's some we can do it on this. So I'll continue with the Faraday's law. Lenz law is used to find induced current or to find of the magnetic field, but Lenz law does not give any information of induced EMF, how much EMF is induced, how many volt EMF is induced. We don't have such information in Lenz law. That's why Faraday's law is used to calculate the induced EMF in volts. Faraday's law is so clear because, remember, induced EMF can be obtained only by changing the magnetic flux. So Faraday's law is about this. If you change magnetic flux in time, so you can induce an EMF in the coil. We know about that. And that's why Faraday's law is negative delta phi over delta N. But if there are more than one loops, so you are going to multiply this by N, you are going to get the EMF induced in this coil or whatever the shape is. So E is the induced EMF, induced electromotive force in volt, N is the number of turns, delta phi is the change in magnetic flux in Weber, delta T is the time during which magnetic flux is changed in second. This negative sign here is coming from the Lenz law, remember? So according to Lenz law, induced magnetic field always opposes the change in applied magnetic field. This opposes as a word is adding a negative sign in here in this Faraday's law. And delta phi over delta T is known as the time rate of change magnetic flux. In fact, this time rate of change in magnetic flux is induced EMF. Delta phi over delta T, magnitude of induced EMF. Yani şöyle bir soru bile sorabilirler. So which of the following is the induced magnitude of induced EMF, which is time rate of change of magnetic flux, is magnitude of induced EMF. Yani delta phi over delta T. And the questions are not so hard here. Just you are going to check, you are going to change the magnetic flux. You will see that magnetic flux can be changed by three ways. You can change the area, or you can change the magnetic field. Most of the questions are about changing area or changing the magnetic field. And then you are going to apply all this. For example, practice problem 2. A coil with 205 turns of wire of total resistance 23 ohm, cross-section area of 0.25 meters squared is positioned with its plane perpendicular to field of a powerful magnet. When the average current, what is the average current induced in the coil during 0.25 seconds? That magnetic field drops. Yes, what changes here? Magnetic field drops, decreases from 0.1.6 to 0. So you are going to write delta phi is the area times delta B. Yeah, magnetic field is decreasing. Final minus initial. Final is 0. Initial is 1.6, so delta B is negative 1.6. Multiply with this area is given. You got delta phi. Divide by time delta T, which is 0.25. Multiply by number of turns, you will get the induced EMF. It's not so hard. You can do it on your own. Next title is the self-induction. But self-induction, before studying the self-induction, I'm going to remind you what electromagnetic induction is, and then we are going to apply the self-induction after that. So remember electromagnetic induction, there was a coil, and then a bar magnet and a coil were relatively approaching or moving away, and then there will be an induced magnetic field on this coil. And in the case of approaching, when there is an increase, and when I make this magnetic field approaching, which means this magnetic field along this coil becomes stronger and stronger. That's why this induced magnetic field becomes in the opposite direction. So, to weaken that one, to keep the total magnetic field constant, that was the Lenz law. So, in this case, we used a bar magnet. We used an increasing magnetic field by moving a bar magnet closer, or a decreasing magnetic field by moving a bar magnet away. But in self-induction, we will not use this bar magnet. We are not going to use an external magnetic field. We are going to use coil itself. Coil itself will induce coil itself will increase the magnetic field and decrease the magnetic field. How? If a magnetic field is applied to the coil by an external source, such as a battery, so if I connect the battery to this coil, so initially close the switch. So of course you have some current and this magnetic flux is and the magnetic flux of this coil. There is some magnetic flux. So magnetic flux is increasing for time. If magnetic flux is increasing, there must be an induced magnetic field. So if magnetic field is increasing, so induced magnetic field must be opposite direction. So blue lines are from right to left, which is the applied magnetic field of the battery. So then induced magnetic field be opposite, which must be from left to right, which is a green magnetic field I draw. So this induced magnetic field, of course, must come from an induced current. If magnetic fields are opposite in direction, batteries current and the coils induced current also must be opposite in direction. So this phenomenon is called self-induction. We didn't use an external magnetic field here. We used the magnetic field of the coil itself, but we used a battery. This opposite magnetic field comes from an opposing current on the coil, which is known as self-induced current. And net current of the coil becomes I external, yani current coming from the battery, minus I induced, yani current induced by the coil. We are going to subtract them because they are in opposite directions. And the creation of EMF in a coil due to the variation of the current in the coil itself. And as you say, we change the current from 0 to a number, current increased in the coil, and this increasing current in the coil induces an EMF. And this phenomenon, inducing an EMF in a coil due to the change in current in the coil itself, is called self-induction. Electric current through the coil can be changed by two ways. One of them is opening and closing a circuit. Yeah, you can make it open. We did here, it's all closed. Or you can do it open also. You can increase or decrease the current. Second one is using a rheostat. Rheostat is also a device which can increase or decrease electric current in this coil. So by these two techniques, by opening and closing a circuit of a DC battery, or by increasing or decreasing the electric current by using a rheostat, you can change the electric current in the coil, and you can induce EMF in the coil, or in self-induced EMF in the coil. So a similar effect is observed in the coil if external current, electric current through the coil decreases by time. Ne demek bu? You can make the circuit off. You can open the circuit, and you can open the switch. So it is closed right now. When it is closed, if electric current is magnetic field is to the left, for example, blue line, when it's closed, as soon as you made it off, this time a magnetic field in the same direction will produce on this coil, because decreasing magnetic field, blue magnetic field will decreasing when it is making opened. So then induced magnetic field will support it by being in the same direction. And there is an equation in self-induced EMF. There is a proof in the equation, but these proofs it's up to you. You don't. But the final equation is that it is very similar to Faraday's law. In Faraday's law, we were getting delta phi over delta t, but in self-induction, we have delta I over delta t. So electric current is changing on the coil by time. So you are going to multiply this delta I over delta t by a constant. This constant is known as the coefficient of self-induction of the coil. And this constant depends on specification of the coil. I mean, we will get the equation in the next title, which is the number of turns, which is the area, which is the medium, which is the length. So all these things will determine the coefficient of self-induction of the coil. And its unit is Henry. This L is called Henry. Equivalent of Henry is volt times second divided by ampere. Volt times second divided by ampere is the equivalent of Henry. So using this equation is not so hard. Just you are going to check that if there is a increasing or decreasing. If is increasing, so delta will be positive. If decreasing, delta will be negative. You are multiplied by L, so divided by delta T, you will find induced EMF in the self-induced EMF in the coil. But as I said that this constant, this coefficient of self-induction depends on the related to specification of the coils. And by using Faraday's law of electromagnetic induction and the second law, which is about self-induction, we can make them these two equal, and then we can get equation, which equation can be used to calculate the coefficient of self-induction of a solenoid. So a solenoid has n turns and length is L, and the cross-section area A has a coefficient of self-induction. Mu is the medium, remember, inside the solenoid. What is medium? Is it air? If it is air, you are going to write here 4 pi times 10 to the power negative 7. And n is number of turns, but squared, as you see, it is squared, and then multiply by cross-section area of the solenoid divided by length of the solenoid. This equation will be used to calculate the coefficient of self-induction of a solenoid. And practice problem 2 is one of the ministry exam questions asked about this equation. Which one leads to a higher increase in coefficient of self-induction of a solenoid? Doubling number of turns or doubling cross-section area? Because here is the square, number of turns is squared. If you double number of turns, L increases by 4 because square of 2 is 4. But if you double area, because these two are directly proportional, doubling area doubles the magnetic coefficient of self-induction, but doubling the number of turns increases the coefficient of self-induction by a factor of 4. That's why N has a higher increase, causes a higher increase in coefficient of self-induction of a solenoid. These questions are not so hard. If the electric current grows in a circuit from 0 to 10, as you see, electric current is increasing. Delta I is 10 minus 0, which is positive 10. Delta I over delta T, so positive 10 divided by delta T is 0.1, which is 10 over 0.1, which is 100. And multiply by coefficient of self-induction with 0.02. So then a negative 0.02, of course, negative is coming from equation. 0.02 times 100, which is 2. Negative 2 is the answer for this one. You can easily calculate them. They are not so hard. Or the same as this one. And in this section, we are going to talk about two small titles. One of them is the Eddy Currents. Eddy Currents. And the second one is the inside story. Eddy Currents are, in fact, this video is explaining it very well. I'm going to show with the video. Okay, now it's a bar magnet. This bar magnet is a very strong industrial magnet. It has very strong magnetic field. Here's the copper block. This copper block is a conductor. Then we are going to drop this magnet towards this copper block. When the magnet is approaching to the copper block, you know that the magnetic flux through this copper block will change. If there's a change in magnetic flux in this copper block, every change in magnetic flux induces a current on this copper block. So then, on this copper block, there will be current induced, which is the circular currents. These circular currents produce an opposite to heat up you are hiding a gun and you're entering to a airport. In this case, it's when you make clothing goes and then from this. So then these guns metal body and this produce a magnetic field and easily detect this magnetic field. And also you detect gold or some other metals underground. So searching the gold or searching some valuable metals underground, so it can be used. And one electric section. That picks up the sound of an instrument and turns this sound into electrical signal. In fact, it's a kind of microphone. Microphone is also doing the same thing. You are talking a microphone, and then you are changing your sound to electrical signal. Electric guitar pickups also doing the same thing. The construction or structure of a guitar pickup and the microphone almost similar. So which first you are going to use a bar magnet. Bar magnet. This is the bar magnet, permanent magnet with N pole and an S pole. And it consists of a bar magnet, permanent magnet, and a coil wound around the cup around this magnet. This is a coil, which is the copper. Copper is one of the best conductor. And guitar strings are made from ferromagnetic materials. So here is the guitar string, but these guitar strings are special. So they can be easily magnetized. And this permanent magnet is magnetizing this guitar string with S pole close side and pole is opposite side. When you hit the guitar string, this string is starting to vibrate back and forth. When it is moving back and forth, of course, magnetic flux through this coil is changing because receding, approaching, receding, approaching, receding, approaching. Magnetic flux through this coil is changing. If there's a change in magnetic flux, what happens? So then you are going to get induced EMF on this coil. This induced EMF is an alternating EMF because receding and approaching both produce a different directed EMF, positive, negative, or something like this. So then this alternating EMF will have a frequency which is exactly the same as the frequency of this vibrating string. Yani you are going to change because you learn in chapter 4 section 3 vibration produces the sound, and then if you transfer this vibration into this coil as an alternating current vibrating with the same frequency, and when you attach this alternating current to a loudspeaker, you will get the same sound, same frequency of the sound from the loudspeaker. So this is how electric guitar pickups work. So they pick up the vibration from this guitar string, converts this vibration into alternating EMF, and this alternating EMF later can send to the loudspeaker.